Hello, everyone. Okay. Hello, everyone, and welcome to this workshop series, Perceptual Models of Dominant Hydrologic Processes Across North America. Before we get started with our speakers today and this morning, I want to give a brief overview of Quasi while folks are getting settled. My name is Julia Masterman. My pronouns are she, her, and I'm the Education and Outreach Specialist for Quasi. Quasi is the consortium of universities for the advancement of hydrologic science, and we're a nonprofit organization funded in part by the National Science Foundation. Our mission is to empower the water community and advance science through collaboration, infrastructure, and education. We seek to fulfill this mission in a number of ways, two of which are our data services and our community services. Quasi Data and Compute Services provide tools and support for the entire data lifecycle. Quasi hosts two data repositories for water science data, HydroShare and HIS. The hope is that by providing these services and the support and infrastructure, Quasi can help researchers formulate and execute their data management plans, be effective data stewards, and meet the requirements of funding agencies. The other side of our organization contain our community services. These include grants, workshops, a summer institute with the National Water Center for graduate students, webinar series and events like this one, a virtual university, and more. This is the first in a series, this is the second in a series of 5 workshops with the morning and afternoon sessions. We hope that you'll consider joining us for the other workshops in this series and this afternoon, or share the word with colleagues who may be interested in courses or in workshops in other regions that we have coming up. Today's workshop will focus on the Western Mountain and Coastal region. Thank you to our conveners for putting together this series of workshops and to CIROH who supported this project. This morning, we'll hear keynote presentations from 4 fantastic speakers. I'll be handing the mic over to them in a moment to describe the work that they do, and to Martin to describe this project as a whole. Thank you to our speakers for taking the time today to join us, and for all of you attending for taking the time to contribute to this synthesis activity. This afternoon, we hope you'll join us for a more interactive session. You'll register for it separately if you've not already, and we'll get that connection information via email. I'll put the link to register for the afternoon meetings in the chat in just a moment. Before we get started, a few logistical reminders. This webinar is being recorded and will be posted on the Quasi YouTube channel. As an aside, the afternoon synthesis meetings will not be shared publicly. Secondly, we ask that you use the Q&A functionality to submit questions to our speakers. So rather than the chat, maybe familiarize yourself now where that Q&A functionality is, and we'll try to get to as many as there is time for. And then there'll be plenty of time for discussion in the afternoon. And finally, we expect that all involved with Quasi events uphold the Quasi Code of Conduct and promote and maintain a professional, considerate, respectful, and collaborative virtual environment. So thank you. Here's our overview of our agenda for the day. Note that we'll have a quick 5-minute break between speakers and lots of time for questions. With that, I will pass the mic on to Martin. Thank you.
Yep, thanks very much, Sarah. I'll just try to share my screen. Yep, here we are here. Okay, and I assume that you can see this correctly? Yep, 2 thumbs way up. Okay, well, thank you. Well, I'm excited to be here today. I'll just start by defining the need. I'm trying to predict threats to water futures that requires comprehensive models that synthesize our understanding of interactions between the natural and anthropogenic world. Some of the key challenges that we have are quantifying sustainable water supplies, predicting water-related hazards, and understanding the role of water in the Earth system. These are wicked challenges that can often exceed the capability of entire modeling groups, entire agencies, and in many cases, entire nations. So a community approach is needed. The National Water Center in Tuscaloosa, Alabama, was set up about 10 years ago and had responsibilities for national domain hydrological prediction. The initial versions of the national water model that they used Earth system modeling approaches, where a land model was applied on a 1 kilometer grid, terrain routing applied on a 250-meter grid, routing on the NHD plus river network, level pool reservoir model. The prediction ecosystem had fairly simplistic approaches for parameter estimation with limited regionalization, also simplistic approaches for data assimilation that were based on direct insertion. Provides information for about 2.7 million river reaches, extending the predictions from the 3,600 points that were served by the RFCs. The initial plans were very ambitious, looking to predictions of water quantity in the first year, water quality in the second year, and predictions of hypoxia in the Gulf of Mexico in the third year. As they're moving forward, some of the prediction challenges became very apparent. There's a number of critiques of the hyper-resolution paradigm. One critique was that the models don't perform well because there's not sufficient information and computing resources to infer the large number of model parameters. Another critique of the hyper-resolution paradigm is that the hyper-resolution models aren't sufficiently agile to simulate observed processes in specific regions. They've got strong constraints, and it can be difficult to simulate the dominant processes across different corners of the continent. Under the leadership of Fred Ogden, who's the chief scientist at the NOAA Office of Water Prediction, NOAA began to develop the next generation hydrological prediction paradigm. The motivation for this was that the siloed approach to hydrological modeling doesn't adequately consider the diversity of approaches at various levels of spatial and process complexity. It's difficult to identify a single model that's best everywhere, best at everything, and best all the time. So the approach in the next-gen paradigm is to construct a deterministic multi-model mosaic that can represent the diversity of hydrological processes across the North American continent. The challenges that we have in implementing this paradigm is that land hydrology is immensely diverse across the continent. And if next gen is to realistically predict local hydrological states and fluxes across this rich hydrologic tapestry, we need to know what processes matter, where, when, and how. So if we've got a deterministic multi-model mosaic, we need some theoretical support for that mosaic, which is a synthesis of hydrological processes across the continent. So that's why we're here today. The implementation of the next-gen paradigm is supported by the Cooperative Institute for Research Cooperations in Hydrology. This is a consortium of partner institutions that are working closely with the University of Alabama to advance research to operations for hydrological prediction. It's a collaboration between academia and government and the private sector, bringing together computer science, domain science, and data science to improve science for society. The scope of this project, as I mentioned earlier, is to define the dominant hydrological processes for a continental mosaic of distinct landscapes. So we're iterating on a couple of tasks in order to move forward. The first is to produce a continental map of hydrological landscapes, described through the juxtaposition of hydroclimate, terrain and geology, and vegetation, land use and management. And then also to develop perceptual and conceptual models for each unique landscape in the hydrological mosaic. And this process synthesis, as I mentioned, provides the theoretical support that's necessary for next-gen developers to simulate the salient processes and features of each unique hydrological landscape across the North American continent. In order to do this, we've brought together a team of people, from diverse backgrounds who can help pull this off. Hilary McMillan, as many people know, has been really a leader in our community in trying to provide a synthesis of perceptual models across the globe. She's developed the Perceptual Model Database, And that database has been really useful for many of us to try to understand the spatial variability and dominant processes across larger geographical domains. Ying Fan at Rutgers University has dedicated her career to hydrological synthesis. She's done a number of really important synthesis papers on hill slope hydrology, on wetlands, on plant rooting depth, etc. And we're really excited to have Ying's power of synthesis to help pull some of these threads together. Katie van Verkhoven is our private sector partner in this project. And Katie has got her eye on operations and is always thinking about how we can take what we're learning from research hydrologists and incorporate those lessons in operational prediction systems. Wouter Knerben is a research associate, senior research associate, University of Calgary, and he's been leading a lot of the efforts in this project to identify what are unique hydrological landscapes and what are the salient features of those landscapes that we need to represent in models. And then our partners from Quasi, Jordan Reed, director of Quasi, is a force of nature, has been able to really push us forward and connect with the community. Julia Masterman has been orchestrating all of these communications in a very, very effective way. We're very, very grateful to her. And Irene Garusi-Najad has been awesome in terms of being able to connect a lot of what we're doing to the process understanding and communities across the country. So where we're at, as Julia mentioned at the beginning, we've got the goal to improve the theoretical underpinnings of hydrological models. We're doing that by synthesizing process understanding across large scales. We're trying to refine initial perceptual models through community workshops and focus regions. That's where we're here, and followed by wider community consultations that will be presenting some of these findings at AGU and asking for the community to refine those findings. Where we are now, we're in the second workshop. We had the first workshop in the Eastern region a couple of weeks ago. That was very, very successful. I learned a lot. We have the second workshop now for the Western region. So I'm really, really looking forward to what we can learn together today. The overall goal that we have is that as we're defining perceptual models of hydrological behavior that provides insight into process dominance. And then from there, what we're learning from these workshops is to select appropriate models for the region or make targeted improvements if no appropriate model is available. And of course, this is difficult. The traditional tactics in hydrology focused on modeling individual catchments, making it difficult to generalize results to large domains and other regimes. The concerns are, is it even possible to generalize hydrological behavior given the unique character of individual basins? Do we lack the necessary information that's required to develop powerful and acceptance explanations? And are the problems of underdetermination so pronounced that we cannot move beyond explanatory pluralism? So we're embarking on the synthesis effort to systematically formulate, organize, formalize, encode, and evaluate hydrological theories. We're recognizing that the community's made tremendous advances over the past few decades in our capability to explain and predict processes, process interactions, patterns, and scaling behavior. But the problem is that the process explanations are currently scattered across research groups, not yet widely incorporated in models, and that we think that we can work with the research community to advance hydrological models by unifying process explanations across watersheds. So that's why we're here today. I'll stop there and then pass it back to you, Julia.
Thank you very much. And I will hand it off to Ying to introduce our first speaker. Thank you.
Yes, thank you, Julia. Thank you, Martin. And Sarah, while we connect you and share your screen, I'm going to briefly introduce the speakers. And we invited 4 speakers today to talk about mountain hydrology from different angles. from the atmosphere to the vegetation to the subsurface and to the feedbacks, integrations of it, of all the drivers to actually yield the stream flow. So the four speakers are known experts on mountain hydrology. Mountain hydrology is really the heart of the CZ, critical zone science. So these interactions are really the focus. Our first speaker is Sarah Goking. Sarah is a research hydrologist at the U.S. Forest Service. Among the many subjects she works on, she studies forest dynamics, such as mortality, disturbance, like fire, diseases, and land use, land cover change, and linking forest water use to the hydrology, because forests depend on water, but also significantly affect water budget and stream flow. So today, our first speaker, Sarah, will talk about mountain hydrology from the angle of forest dynamics. Sarah, is all yours.
Thank you, Yin. I'm very glad to be here. Thanks to Quasi for organizing this. I want to just note that as I look at who is here today, almost every name that I recognize is someone whose work has influenced how I think about hydrology and forest hydrologic processes. So it's a pleasure to be here. Also, for those of you that are with government agencies, my title is not research hydrologist, but that is a lot of what I do. But I do, I know that means really specific things in government contexts. Nonetheless, I have done a lot of research on hydrology and forests, and very glad to be here. So I'll be focusing on the Colorado River Basin. And to tell you where we're going, just so you know, the lay of the land in this presentation, here are the three main points of my presentation. First is that evapotranspiration, or ET, is a dominant flux, second only to precipitation in most parts of the Colorado River Basin, and indeed many other arid catchments. ET may change as a result of vegetation change or land cover change, but individual ET pathways may counteract each other depending on structural and climate controls. And I'll talk about what those controls are. And also, trees and other vegetation sometimes function as straws and sometimes function as structures. So those are different types of controls on various components of ET. So now to orient to the Colorado Basin, this is a large river basin. The Colorado River itself is over 2,000 kilometers long. It drains 7 US and 2 Mexican states. And the river is already over allocated relative to the amount of water in the basin. The land cover is diverse in terms of structure and hydrologic function, ranging from dense coniferous forests in the high elevation headwaters to very sparsely vegetated areas in the Mojave and Sonoran deserts in the lower basin. The climatology is really as dry as a lot of the basin is. It's really all about snow. Most of the runoff comes from seasonal snowpack in the upper basin headwaters catchments. The lower basins catchments are very much warmer. Again, sparser vegetation produce less of the runoff. And again, I mentioned ET is a dominant process. Runoff efficiencies or runoff ratios, so Q over P, are generally less than 10%, ranging up to about 50% as a maximum in the headwaters. So of course, the biggest flux is precipitation, and it varies a lot temporally and spatially. Most of the precipitation falls as snow between about October and April or May. Some areas in the southeastern portion of the basin also get a lot of monsoonal rain between July and September. And although I'm not focusing on that as a dominant control here, I do want to mention that monsoonal rain is important because in places where it occurs, infiltration excess runoff is a huge process and can produce really destructive floods that are often far from where the rainfall actually occurred. And we've seen that multiple times this year. So the key storage components, the big one is that seasonal snowpack in the upper basin. Another one is interception or intercepted precipitation. Some studies from a few decades ago in Fraser Experimental Forest and surrounding areas found that up to 50% of snowfall can be intercepted by dense coniferous forests. And that component of storage then influences sublimation as well. How much snow is offloaded to the snowpack versus redistributed by wind and potentially sublimated. Soil moisture is another storage component, but it is quite spatially and temporally variable. And the duration of that storage can be quite short. There can be really extreme moisture deficits in a lot of places for most of the growing season. And then groundwater, I'm not going to say a lot about groundwater. As a forest person, I'm thinking mostly about what's going on above ground and what we can measure there and what we have measured. But estimates are that between 10 and 30% of surface flow is derived from groundwater in the headwaters, with much less at lower elevations. So again, the main flux and the main thing I'll be talking about is evapotranspiration, or ET. So where runoff ratios are low, that is the main control on what happens to water that falls from the sky. Is it lost to ET or does it become runoff? And the magnitudes of the various components of ET vary widely and often determine those runoff efficiencies. So the components of ET, just a quick introduction to those components. There's transpiration, and transpiration from canopy overstories versus understories, which is just the vegetation beneath the canopy, can be quite different. There's also evaporation of canopy intercepted precipitation, both in the upper canopy level, the overstory and the understory, and also soil evaporation and evaporation or sublimation from snowpack. So one site that has been well instrumented and well studied in the Colorado Basin is the Fraser Experimental Forest in Colorado. And I think of this as a energy limited forest. So as a forest person, I think about energy and water limitation, and they're similar, they're analogous definitely to how you would think of energy or water limitation in a Budico hydrologic framework. So in more energy limited systems, such as this high elevation catchment in the Fraser Experimental Forest, this is, I'm thinking specifically of Fool Creek, transpiration from forests and also sublimation of canopy intercepted snow are dominant ET processes. In more water limited catchments, lower in the Colorado River Basin, the ET fluxes, other fluxes are more substantial. So they might be soil evaporation or transpiration from grasses or shrubs. And the green areas in this map roughly correspond to areas with forest. So there are some controls on the magnitudes of these ET fluxes and the storage components. And for the purposes of a perceptual model, I'm thinking of them in two categories. One is biotic control, the vegetation. So trees can function as straws. Trees can also function as structures by influencing energy and wind. And then canopy strata, the overstory canopy versus the lower growing understory, can function as different types of straws and structures. There are also what I'm calling abiotic controls, climatic controls, so not biological mechanisms. And the ones that I'll talk about today, a little bit about wind, solar radiation, and a fair bit about aridity. And if you're familiar, some people that study forests use vapor pressure deficit, which is pretty closely related. So In the upper right, coming back to the Fraser Experimental Forest in Colorado, this is Fool Creek. This is one of the well-studied watersheds there where trees have been harvested in clear-cut patches. This is many decades ago. I think this picture was taken probably 50 or 60 years ago, showing different arrangements and sizes of clear-cut patches in that watershed. And the effects of that treatment were determined to really be driven by the two ET fluxes that I've shown here. So I'm showing T subcanopy, that's the change in canopy transpiration, and then delta S subcanopy, the change in sublimation of canopy intercepted snow. So there are also evaporation fluxes, and then there's a whole set of understory and soil fluxes as well. But it's those two big fluxes from the canopy that are the ones that are that were found and really drove increases in streamflow following the treatments shown in this photo. So of course, if total ET decreases, runoff increases. So in that case, trees were functioning mostly as straws, but they also function as static structures. They do intercept snow. They also block solar radiation and deflect wind. All three of the photos that I'm showing here are classified as coniferous forest in the National Land Cover Dataset, but they have very different densities. And also lots of other things that are, different. They might have different rooting depths. I mean, I don't know that for sure, but they're just even looking at them and then looking at the measurements we've taken in those forests, they're quite different densities. Trees have different growth rates and thus probably different transpiration rates, but they're all coniferous forests. The density and the spatial arrangement of trees matters. We know that at fine scales, spatial canopy arrangement affects snow accumulation, snowpack ablation, and soil moisture. So this is both via shading, via uptake of water, and also via the effects of canopies on the ability of lower growing vegetation to take advantage of soil moisture and radiation. So I know Jessica and Adrian have both done a lot of work showing the effects of tree density and arrangement on snowpack. So I won't talk much about that, but given that we know those effects exist, it's also likely, it stands to reason that there are similar effects on soil moisture. Where the snow lasts the longest likely has the greatest soil moisture at the beginning of the growing season, and trees functioning as structures will affect how fast soil moisture depletes throughout the growing season. So trees are not only, they can not only be thought of as static structures, but also dynamic structures. The last decade or two have been quite dynamic in the forests of the Colorado Basin and in many other semi-arid and arid places around the West, as we've seen climate-related disturbances caused by wildfire, insects, heat, and drought. So once we see these structural changes, so even something that doesn't remove the entire tree, so it's not a severe wildfire that consumed the entire tree, it's not a harvest that removed it, often the tree is still there, but the canopy is lost. So even within a single land cover class that does not change to non-forest, you can see partial death of the tree canopy. And solar radiation, precipitation, and wind all can infiltrate the canopy and reach the ground surface better than they could when the canopy was intact. And that has effects then on the evaporation and transpiration from lower canopy strata. And I will mention that I don't think we know what numbers to put on those relative fluxes. There are a few isolated places and the patterns are not, we don't know enough to generalize across broad areas about those magnitudes. So forest canopies also can be dynamic in shifting quickly from wildfire or insect outbreaks or harvests, or they can shift slowly due to drought or heat. And they might shift from canopies to sparse vegetation with little tree cover, or to grasses or shrubs with various densities and leaf areas. And sometimes they can actually grow quite rapidly. Sometimes there might be advanced regeneration of young trees in the understory that once the canopy has died, they grow really rapidly and transpire a lot of water. Disturbance, however, is typically slower than the process that removes the canopy. I like this, this perceptual model here. The paper that produced, or the author that produced this diagram, showed the direction of a lot of these fluxes. Did they increase, shown in dark arrows, or decrease, shown in lighter arrows? So wind speed increases, both winter and summer. Albedo decreased. Solar radiance to the ground increased. And even though the canopy transpiration decreased by a lot, basically went to zero, transpiration from the understory and also soil evaporation increased. The hydraulic redistribution and soil water recharge from this study, which included a lot of detailed measurements, decreased after the canopy died. So this is one example of a study where we can actually put some, maybe the order of magnitude or maybe relative proportional sizes of those fluxes. So at this point, hopefully it's already kind of somewhat obvious that these different ET pathways matter, and that they can actually change from dominance by the canopy pathways to others. And there can actually be compensatory ET responses following a change in land cover or forest density that drive the net effect on ET and runoff. So again, the previous perceptual model, the one that was in my mind when I started doing this kind of research and asking questions about this, was that the canopy fluxes really drive everything, that they were the largest fluxes, shown here with the blue arrows. And both of these diagrams illustrate a conceptual response to a decrease in forest cover. So a decrease in forest cover means those big canopy processes decrease by a lot, and the other understory processes increase by a much smaller amount. And what we're seeing in some research in the last decade or so is that sometimes that is not true. Now I'm going to talk a little bit about climatic controls on ET and on climatic controls on response of ET to forest change. In this paper, we looked at 159 camels watersheds across the United States, across a gradient of aridity, and found that as aridity increased and also as mortality increased, stream flow change, the magnitude of change was greater, and it tended to decrease in more arid watersheds, even though it increased in the wettest watersheds. And we found a similar result for incoming solar radiation. Everything I'm showing here, this is based on observations from the camels data set, combined with forest data. We did something similar for incoming solar radiation and found similar results, but the relationship between aridity and stream flow was a little bit stronger than incoming solar radiation. So I just want to mention that we could think of both of those things as potential climatic controls on that response. So now I've mentioned a lot about what we do know. There is a lot that we don't know, including how arid is arid enough for climate controls to influence ET. What are the typical magnitudes of compensatory ET fluxes after forest change? I haven't said a lot about wildfire, but at a certain severity of wildfire, it goes from a mere canopy removing disturbance to an infiltration modifying disturbance. And I'll talk about that in just a minute. I haven't touched on what's going on underground, which I think is another not well understood aspect of forest hydrology in the Colorado Basin. And then what types of data inputs might we need to move from perceptual to conceptual and eventually forecast models? So the first question, how arid is arid enough? We found in our large sample study an empirical value of 2.35. That's the point at which the relationship between mortality, the severity of mortality, and the stream flow response was flat. At aridities above that value, increasing mortality led to decreasing stream flow. And I think that there's a lot more to be done to confirm this response, determine whether there is a threshold that can be applied and extended to other regions. And you know, just moving from knowing what's the direction of the response to can we actually predict it quantitatively? So a lot more work is needed to confirm that, I think.
Magnitudes. Oops, can you still hear me? Okay, good. Just got a notice to check my audio devices. Okay, so these compensatory ET fluxes can be quantified using eddy covariance methods. And in this study, Joel Biederman and others did just that. And they compared an area with forest cover loss due to mountain pine beetle to an undisturbed site and found that vapor loss in the disturbed stand was greater throughout all seasons than in an undisturbed stand. So I think that's an example of how we can answer questions like that. Eddy covariance studies can tell us a lot about those different ET components. And the reason why this is important is that the magnitude of changes in those different ET components will influence the net effect on ET and thus the effect on runoff. In this example, this is from the Great Salt Lake Basin, actually, which is just next door from the Colorado Basin, where we have additional transpiration on the right-hand side, additional transpiration from new growth and sublimation from exposed snow after losing canopy. That led to a decreased runoff response in that perceptual model. I haven't said a lot about wildfire, but again, I do want to mention, here's a warning from the National Weather Service that following severe fire, there can be a hydrophobic layer that dramatically decreases infiltration capacity of the soil. And we see this lots of places where there is fire, heavy rains, and then both erosion, sedimentation, and flooding. And I think it would be useful to quantify at what levels of fire severity does that occur? Is it something that can be incorporated into models? And then what's the longevity or the duration of the effect on infiltration? I haven't said much about what's going on underground. I admit that is not my area of expertise, but there is a lot more we could learn about infiltration capacity and water partitioning with respect to rooting depth and water depth amongst different canopy strata. And most studies of forest change effects on runoff don't account for like different substrates or underlying geology. What types of data then would we need to move from perceptual to conceptual and then eventually forecasting? First, moving beyond land cover classes. You know, I showed 3 different coniferous forests that might all be parameterized the same in hydrologic models, and not all coniferous forests or whatever other land cover class are equal. But what is the appropriate spatial resolution to show canopy density and structure? We want to represent them at spatial scales that are parsimonious, but still represent key controls on ET fluxes. And then lastly, representation of wildfire and even of different severities of wildfire might warrant being treated as a unique type of land cover change because of its effect on infiltration. So previous perceptual models followed what's summarized here in this 1967 review paper, that there was an inverse relationship between forest cover and water yield. So reducing forest cover would increase water yield, increasing forest cover would decrease water yield. And I really like this third statement. Response to treatment or disturbance, I would say, is highly variable and for the most part unpredictable. We have seen some studies suggesting that that dashed line might actually be the relationship that exists in more arid watersheds. So the big question is whether this is true, whether it's true in a universal or extensible way for other arid catchments, and then what are the magnitudes of the various ET pathways and how do they change in response to the types of climate-induced disturbances and subtle land cover shifts that we're seeing in the Colorado Basin and other arid regions. So now just to bring it all back to where we started, the main points that I hope you walk away with are that evapotranspiration is a very dominant flux in arid systems. Most of the precipitation that falls from the sky is lost to ET. ET might change as a result of vegetation changes, even subtle ones, but individual ET pathways may counteract each other and lead to potentially unexpected runoff responses. And those responses and individual pathways depend on the structural and climatic controls that I've described. Lastly, trees and other vegetation sometimes function as straws and sometimes function as structures. So figuring out, when is what type of function is actually controlling in any given system is a good, that'll be a big missing piece to figure out. So I will stop there and thank you for your attention.
We're open to questions. Thank you so much, Sarah. That was really insightful. And as we continue the keynote talks, and the audience probably notice they're not really per se talking about their own work, but really a higher level of what we know, what we don't know, and keep that in mind so that those talks will be our jumping boards for our afternoon discussions. I'm going to have Irene pass it to Irene to handle the questions and answers.
Thanks, Yin, and thanks, Sarah, for your great presentation. Everyone, please feel free to use the Q&A box to post your questions. We haven't received any questions yet. Once we get one, I will read it for Sarah. And then, okay, the first question is from Dave Turbotten. And what are the measurements you think are needed to make most advances in this area? ET, canopy information, stream flow, or other things?
I think that there are probably, I actually think eddy covariance measurements are the most promising. I know that there are finer scale measurements that can be taken, like the scale of an individual leaf. And there's also a long history of challenges on how do you scale from an individual leaf even to a single stand. And if you're not a forester and you haven't heard stand used in that way, just an area, a place on the ground, maybe half a hectare to a hectare or larger. How do you scale from that leaf higher? And I think eddy covariance methods are well suited to matching the scale at which we're measuring the vegetation structures themselves. So I think that's probably the most promising.
Thank you. Okay, moving on to the next question from Safiq Khan. Good summary, Sarah. Given your role in Forest Service, I was wondering if you can speak to challenges in verifying some of the fluxes you mentioned. In my experience, pairing is hard and introduces large errors.
Yeah, that's good question. First, I'll come back to my first answer, which really, you know, if you're not going to do paired experiments, I mean, the paired experiment, you know, is integrating a whole lot of things, including all of those ET components summed to the net effect on stream flow. And so there are lots of finer process level responses of individual ET components that can't be teased apart. They can be hypothesized, but not verified without measurements of those individual ET components. There's also, you know, the promise, the optimistic promise of remote sensing based ET, which I think there could be some creative substitution of space for time to try to estimate the effects of a land cover change or even a subtle shift in canopy cover. But I think we're still trying to figure out how reliably we can rely on remote sensing based ET to accurately integrate all the different ET components. And a lot of those ET models are based on the same things that are, you know, it's sometimes challenging to separate a rapidly growing short tree canopy from, say, a grassy area. So that raises more questions about, you know, what's the level of detail at which we can use remote sensing ET to assess those changes.
Thank you, Sarah. Yeah, so the next question we have from Ryan Webb. Great summary, Sarah. For the aridity index, it can be really sensitive to the equation to calculate PET and then choices for variables in PET. Do you recommend a specific method or approach based on your work?
The best one. That's a tongue-in-cheek response. It's not a great response. I was rather opportunistic in my work and used what was in the CAMELS data set for those watersheds, and then did actually use the Hammond method to estimate PET for specific time periods if I wasn't looking at long-term PET. At finer scales, if you have more detailed measurements on winds and temperature, of course, I think that's better. But that's not always possible, especially when we're talking about trying to look across many watersheds and find patterns that are universally true.
Thank you so much. And we have a very engaging Q&A and the chat box. So are we good on the time? Can I go with the next question, Julia?
Yep, last question,
okay.
Probably.
Great. So the next question we have from Water. A number of large domain hydrologic land models use a big leaf simplification to model canopies. Given all you talked about, do you think that it is a workable approach still, or does that miss too many nuances in regions like this?
That is a great question, and I think it does miss too many nuances. I think that's great if the main function of the trees is functioning as interceptors and straws. And when I say interceptors, you know, mainly of precipitation. But when the solar radiation, you know, blocking solar radiation, deflecting winds, and PET is so high, I think those factors become more controlling. So it's not one big flat leaf, you know, the arrangement and density start to really matter in more arid regions. So the dragons are in the arid regions, I think.
Sarah, the next question is from Alain Rousseau, and my apologies if I didn't pronounce it correctly. Variations in water storage from year to year matters a lot with respect to changes in annual runoff. Should not we focus more on soil moisture storage and groundwater storage? In other words, it takes more than 1 year of above normal level of precipitation to overcome long-term low flow conditions. that is annual runoff.
Yes, and I agree with all of that. I think how much water ends up in the soil and then potentially becoming, recharge for groundwater, though, is controlled to a large extent by canopies functioning as structures. So again, the runoff ratios in these really arid regions are so low that it's hard to quantify what is even available for soil moisture storage and groundwater recharge without understanding those controls.
Great. Yeah. So next question is from Martin Clark. To what extent do you think that forest disturbance, such as disease, fire, is a dominant hydrologic processes that need to be represented in mechanistic models? What might we be missing by ignoring forest disturbance in our models today?
One thing, a big one, I'll come back to the example of severe wildfire. And if you're trying to forecast, say the effects of a monsoonal rainfall event in southern Colorado or southern Utah, the Four Corners area, we're missing a lot, and I don't think that we would be able to accurately predict some of the magnitudes or maybe the runoff or the erosion and sedimentation effects of some of those events in forested watersheds after severe wildfire. We're seeing that in the Sierra Nevada and California as well. Lots of places in the world where this is occurring. So that's one thing. The other thing is in forest research, it's at this point sort of acknowledged there are big changes going on in forests worldwide. We could spend an entire series of workshops talking about that. I'll refrain from doing that, but I'll say those changes are big. And if a change in land cover type is sufficient to warrant, changes in the way that if it's simulating changes in runoff and stream flow, we're seeing forest changes that can result in land cover change or even shifts within a cover class that are substantial enough to really impact what we're trying to model.
Yeah, we are running out of time, and to respect everyone's time, I'll encourage you to post your questions, and there's one question left. I'll send it to Sarah, and if you could answer that in the chat, that would be great. So we can move on to our next speaker. Ying, back to you.
Yes, and for those of you who have questions, didn't get a chance to ask, please join us in the afternoon. We'll have plenty of time to discuss that. But we need to move on. And our next speaker is Jessica. And while you share your screen, I will have a brief introduction. Jessica is a professor in hydrology at University of Washington. And Jessica is widely known for her work in complex terrain, mountain terrain. And I remember reading an article years ago about cold air descending into valleys, forming very different microclimates that is just cannot be explained. It does not, it's just the average climate of the grid cell, it just doesn't actually, it's not very meaningful. I also remember seeing a picture of her climbing a tall tree and installing sensors. So Jessica works on a variety of subjects, but she's going to talk about the mountain hydrology from the atmospheric perspective, the climate variables that drives hydrology. There's so much uncertainty, yet they are so critically important. So she will talk about the mountain hydrology from the atmospheric perspective and the associated high flows. With that, Jessica, the floor is yours.
And are you seeing the screen you want to see? I can never tell which of my screens you're seeing.
Yes, we are seeing a shared. We're seeing the two. There's a note.
You're seeing the notes one. Hold on.
Yes.
Hold on a second. Let me just reshare it there.
That's better. It's working now.
It's working now.
Yes.
I don't see anything right now. That's interesting.
Yeah, if you can just go to slide projection mode.
Now what do you see?
Oh, I see back.
Now we're seeing the speaker notes. If you on the upper left corner, there's a button swap displays. That might fix it.
There's the upper left. Oh, swap displays. Got that one. How's that?
Oh, that's great. Thanks.
That's what you want to see. Awesome. Okay. Excellent. All right. Still seeing it? What?
Yep, looks great.
Every time I push a button, I worry. Okay. So I was given the task to talk about perceptual hydrology, and I realized I hadn't been keeping up with the recent literature, and so I didn't know what perceptual hydrology was. So like any good person, I type it into Google, and Google AI explained to me, because I wasn't sure if it was different than conceptual hydrology. They said conceptual hydrology is based on empirical equations, and perceptual hydrology involves drawing pictures, sometimes with dragons. So I only put dragons on the first slide, but I wanted to talk about rain. I noticed none of the pictures had rain, so I put my dragons in the rain with some flooding. So we're talking, there's a lot of different regional workshops, and today we're focusing really on the western half of the US. And you start making some just general plots of the distribution of runoff across the US, and you see that things are actually really smooth on the eastern half compared to the western half, right? Our spatial distribution of runoff gets really, really complex. Sarah is talking about places where ET is much more than precipitation, and I'm living here in this green area where we actually have an extratropical rainforest out in the Olympics, and we have a lot of runoff and a lot of rain, but it's really drastically different. If you just drive across Washington from one side to the other, we have incredibly different hydrology. And this map of where the runoff is really relates directly to the rainfall. You can see the extreme just variation in rainfall, particularly in Washington, where I'm hanging out these days, but throughout the West. And Sarah showed, for Colorado, the headwaters versus the lower elevations. And really, this variability in the spatial distribution of precipitation is absolutely key for us to get into any drawing we do of the hydrology out here. Beyond just being variable in space, we also have really variable precipitation in time. So again, if you look at even the eastern 2/3 of the space of the US, you see we have fairly uniform rain by month, or we have actually more rain in the summer, which is when the plants want to use that water to grow. Now, when we go over to the West Coast, we see we have this really strong Mediterranean climate. All of a sudden, you see that all of the rain comes in the winter and none of the rain comes in the summer, particularly in California. I once stood up in an international meeting and said it doesn't rain in California in the summer, and they didn't believe me. I said, really, I grew up there. It never rains in the summer. Even Raleigh, Seattle, right? It all comes in the winter. And this results in hydrographs that look something like this. So these are two rivers in California, the Smith on the coast, which is all rain-fed, which is the blue line, and you can see the runoff is coming when the rain comes, and the Merced River in the Sierra Nevada, which is snow, and you see that the runoff is coming when the snow melts. But this, is an incredibly different runoff pattern, and the story out here is really rain versus snow. So given what other people are talking about in this section, I decided to focus on these western regions and on these wet months. So remember, these are times and places with a lot of precipitation and a lot of precipitation at once. And my other colleagues will be talking more about the snow in the summertime, but let's just think about what's happening with these floods in the winters. Okay, so for my perceptual model, it's wet. It's been raining all fall. It's winter. The soils are close to saturation. For the mountains, these soils are not very deep. And really, here's the perceptual model. No one in my family has a degree in science, and after 5 years doing my PhD, my cousin said, so it took you 5 years to figure out that snow melts and water runs downhill. And I said, really, yeah, that's about it. That's really what I do. Also, let's add to that rain falls and contributing area matters. But in this time of year, really, there's a quick transfer of input to output, and you don't need a lot of advanced subsurface hydrology, if you get the right amount of water in and the right area over which it falls, you actually get really close. So, but why is that tricky, right? This seems like a trivial thing. This is a nice graphic by Mark Raleigh. Here's your sort of typical storm in the western US mountains. And you can see we get snow on the top of the mountains and we get rain below that. An area contributing to the winter storm is really the area receiving rain, right? The snow is storage for later. Now you get a slightly warmer storm and your snow line goes higher. And all of a sudden you've got a lot more area contributing to storm, to runoff. And more than anything else, this is the #1 factor you need to figure out for your storms. So again, fundamentals, peak flow rates proportional contributing area is proportional to melting level elevation, thus the peak flow rate is proportional to the melting level elevation. So this is a nice paper by Alan White back in 2002 for California, where he just made a plot of peak flow rate in California rivers as a function of melting level. And you can see it's going up by factors of 2, 3, 4. Like these are huge changes. And so your #1 thing you need is to get that area where rain changes to snow. And again, here's a picture of the Western US. This is the atmospheric river, which is the flow of moisture upstream. This is what delivers the biggest storms. These are masses of moist, warm air that are raining typically at higher elevations than your typical storm. And the reason we get these floods is because much more contributing area is in a given storm. Okay, so the first thing in terms of how should we change our perceptual model is let's extend our perceptual model so it's looking atmospherically upstream at the storms that bring the moisture. And you can see I took the USGS graphic, and then because I live on the West Coast, I just flipped it. So it's a mirror image of whoever was on the East Coast and drew this. Although their mountains aren't this big, I'm not sure what they were thinking. But there are other things, soil, water, and groundwater. Again, these are matter over the course of the year, but for the winter, we can mostly say they're saturated and the runoff is fast. And it's really these atmospheric controls that are going to control our runoff and our floods. So here's, another drawing. Again, you want to understand the atmospheric river and the upstream boundary. You want to understand exactly where that's coming in. It's very narrow. Which watershed it hits is going to determine what is going to flood. You need to understand how that moisture intersects with the mountain range. The mountains control the hydrology quite a bit. You can have a barrier jet that blocks the air and makes it rise upstream of the mountains. You can have the air completely blocked by the mountains, like flow #2, or it can go around the mountains. What are the pathways? And this ends up being the dominant factor on a lot of the storms. Beyond that, you need to understand, the microphysics, what makes a snowflake turn into a raindrop, the phase, when does it shift, which is not trivial, and then where is that rain or snow deposited on the land surface. Just, one more sketch. I made this one, and then this was for a paper done by a graphic artist with more talent than I am, showing, that again, how the storm intersects, what's happening with a warm front, a cold front, how does that intersect with the mountain is important to know. Is there blocking? Where is the 0-degree sea line? This is a simple representation, but it actually curves and changes as it intersects the mountains. Where do you get embedded convection with more uplift within it? And how does all that change your rate and location of rain and snow? Okay, so to summarize that in a simpler way, really, if you want to model floods, you primarily need 2 things. 1, how much precipitation. 2, is it liquid or frozen? So not that hard, right? Except you start with how much precipitation. So Sarah was showing the AT was off by 30%. The amount of snowfall you get is off by 200%. This is really hard to do. You go out and put, I forget how many different sensors they have out here, like 6 or 7. They put 6 or 7 different sensors all next to each other near Boulder, Colorado. And this is what they all measured, off by more than a factor of 2. Also, this is a photo by Nick Wayand, who was a student of mine who says conditions that are good for snow are bad for instruments. There's more photos. It's hard to do. Beyond that, we take these measurements, as they are. And then what we typically do is we take all these point measurations and then we put them together as input data into a gridded precipitation data set. And we call this truth. But really, this is a bunch of these observations based on statistics and interpolation. We use this both as input data to all of our hydrologic models and as benchmark data for all of our atmospheric models. So this is a really critical point in everything we're doing. But how good are these gridded precipitation data sets? And again, we can use our perceptual model in a testable hypothesis, and we can say, all right, averaged over space and time, we would expect that, over long time, that this, storage, soil, water, groundwater, ET, got to be greater than 0, right? It's doing something we can't quantify it exactly, but it's something. So we need more input, rainfall and snowfall, than runoff output. Averaged over long time scales, we would presume that some water is lost back to the atmosphere and we should get less runoff than rainfall and snowfall. So we can pose this question and then take a look at all these gridded precipitation products. And this is kind of too much to put on any table, but what I want you to note here is that there are a lot of different gridded precipitation products you can get, but for the US, almost all of them are based on PRISM. You can see that there's PRISM, and then everything except AMET uses PRISM as its gridding baseline. So they're not really that different at the core. However, if you plot them all, they still manage to be quite different from each other. So subtle differences in how you're choosing which stations to include and over which periods you're averaging when you do quality control and throw a station out can lead you to very different, this is just long-term climatology of precip in the Western US mountains. And so this is what PRISM shows. And then this is the difference of various other data sets. And they vary plus or minus 20% for mean annual precipitation. They're worse in a particular storm. And you can see again, where they're the worst are these, wet mountain areas. They diverge quite a lot. To zoom in the Sierra Nevada, which if you're not great at subsurface hydrology, the Southern Sierra is a wonderful place to go because it's like a granite parking lot. Everything is granite. There's some fracture flow, but really very, very little storage. Things run off. And so here are, again, 6 different data sets for the Southern Sierra. And you can see how, and this is total water year precipitation, so summing up all the storms, how different, the locations and amounts of the precipitation are. Also, if what we've got here is a plot that's showing the blue is the observed annual runoff from the gauge. And all of the other lines are various estimates of basin total annual precipitation, just summing up over from the gridded data set. So this is for the North Fork American River in Northern California. This looks pretty good, right? Precipitation is better than runoff. Cerrus trees are still alive. They have some water. But we go to the Southern Sierra, which does have trees, remarkably, even though it's mostly granite. And the precipitation totals are quite problematic. This is a really remote region. There are very few precip gauges. Those precip gauges are subject to heavy snow, and they're getting destroyed quite a bit. Again, this blue line that's right here in the mess of other lines is the amount of annual runoff. And consistently over all the years, there's just not really enough precipitation. Now, this I don't really have time to go into at all, but if you are trying to match your hydrology model to your precipitation, these different green, so this is precipitation that we thought would be the best precipitation for one of these basins. The different green symbols are different conceptual models for Martin's ensemble of views. You can say, I want 1 bucket, I want 2 buckets, I want my buckets to talk to each other, I want various things you would put in your conceptual hydrologic model. And if you just assume those, and then we varied over the entire parameter space and iterated, the uncertainty, each of these widths is the range of precipitation we would expect due to parameter uncertainty. And then each one of these is just due to changing the model structure. So if you are simultaneously trying to understand the amount of precip in a place that's not well defined and how you should set up your hydrology model based primarily on runoff as the only thing you have measured, it's a really, really big challenge. And this is a basin that's mostly granite. So again, it's relatively simple in terms of subsurface hydrology. Okay, so, well, I'm sure I encouraged you on how much we know how much it rained in the first place. But let's move on to, is it rain, is it snow, or is it something in between? And in the Pacific Northwest, we have this symbol you get in your weather forecast, which is wintry mix. And you know, when the forecast says wintry mix, that means you do not want to go biking. I moved here from Boulder and was really proud of myself. I could bike in the snow, and I realized I could not bike in wintry mix. It is very dangerous. Rain, snow, sleet, ice, don't go out. But that's what you need to forecast in your hydrology model. Where is that changing? This depends on a lot of things, but we can simplify it by saying it depends on temperature. So this is a really nice study from the U.S. Army Corps of Engineers in Snow Hydrology 1956, where they had people sitting up at Donner Pass all winter, just going outside every hour and writing down temperature, and is it raining, is it snowing, or is it wintry mixed in between? And so while there's, you know, a fair bit of uncertainty, it's the 0 to 3 degrees C is where you get wintry mix. Above 3, it's pretty much all rain. Below 0, it's pretty much all snow. But there's this range where you get some of everything coming out of your clouds. Now, in terms of the hydrology, here's the Pacific Northwest, Washington, for example. So here again is our timing of precipitation. It's a Mediterranean climate, so we get all our rain in the fall and winter, and it's sunny and lovely here in the summer. And you can see that for 3 different basins around the area, the timing of the runoff with the same rain is really depending on its mix of, is it getting rain or is it getting snow? So the Skagit River is high elevation, mostly snow. You can see its runoffs coming in the spring. The Puyallup River down by Mount Rainier is kind of a mix, it gets half and half. And the Skokomish River out near the Olympics here is almost all winter rain. But you can see these drastic changes in when the water is delivered based really just on the temperature regime. Okay, so when I first came to Washington, Alan Hamlet was in the office next to me. And he said, okay, I'm simulating stream flow for the Snohomish River. Here's winter, here's spring, stream flow, 3 meters per second. Here are my observations, and here's my simulation. All right, and he was having a horrible time because he'd been tuning all aspects of, you know, the storage, all of the typical things you would tune in your hydrologic model. And no matter what he did, the model was just too cold, really, right? You see there's that the simulation here has too much snow, right? Too much runoff in the spring, too little runoff in the winter, and the real world has more winter rain. Okay, so beyond the precip, what else do we need in our perceptual model? We typically come up with some idea of how does temperature change with elevation, right? So we generally do this with a lapse rate where the average decrease over the world is 6.5 degrees Celsius per kilometer. We measure our temperature at sea level, extrapolate it up. Where's that 0 degree sea line? And then we say, okay, up here stored as snow, down here is rain. Except this also varies hugely. The actual, you know, range of this lapse rate can be anywhere between 3 and 9.8 degrees Celsius per kilometer, which means that elevation of rain versus snow could be anywhere from way up here to way down here on our mountain, right? Giving us drastically different amounts of runoff in a river at different times. So basically, Alan at that time tasked some students and said, okay, for your class project, go look into the temperatures around Washington. And this is just an anecdotal story of how we put our models together and how we make our understanding. So they said, okay, here, this is year, this is elevation, and this is just lines where stations in Washington State happen to have data. And you're trying to find long-term climate stations that would be robust. And they found, okay, the only Paradise at Mount Rainier has a long station, and then Mountain Passes have long records. So if you visit Washington in the winter, if you fly in to Seattle, you might see, here's Mount Rainier, and you often will see there's cold air trapped east of the Cascades. And you can see that often with the cloud layer. So here's Mount Rainier, and in winter, all the cold air is trapped just east of the Cascades. It's really cold there, it's warmer over here. And if you keep looking out your airplane window, you'll see that this cold air from the east also penetrates westward via the mountain passes. So you can see that cold clouds moving in through the pass to the west. So that the Cascade Passes, and this is a paper by Jim Steenberg from '97, they have cooler winter temperatures and more snow than other similar elevations. So here's in the winter, here's Paradise at 1676 meters, Stampede Pass at 1209. It's on average 2 degrees C colder due to this cold air coming in from the east. So the students had this data available. Really, they only had 4 high sites with a decent amount of data. And here is a MODIS image from that same day I was showing you pictures out of the airplane window. You can see where the clouds are. And the students, they looked at it and they said, Paradise in Mount Rainier really looks like that looks really different from the other 3 sites. So we'll presume that something broke there, it's in the mountains, and they threw it out as an outlier. Now look at this one more time with color relief. So here are all the low clouds, that's where the cold air is. Here are where all the stations are. The stations are all in these mountain passes with extremely cold air. This is true not just of the Pacific Northwest, but of mountains everywhere. We have measurements in mountain passes, which are not representative of the majority of the mountain passes are very unique climates and environments. Here's just zooming in one more time. So using these 3 stations and their elevation, they calculated the lapse rate and found on average temperature decreased 6.5 degrees C per kilometer, except that was the lapse rate already in the model. And the model was too cold. It had too much snow, and the real world had more rain. And if you can see, if they had fit through Paradise instead, they would have raised that rain snow elevation quite a bit. And so this is just a paper by Justin Minzer, who looked at lots and lots of different sources of data and found the average lapse rate should be -5 degrees C per kilometer, and that fixed the problem. But this problem remains very common, that we have misrepresentative point measurements of the weather. So moving on to conclusions, the point I want to make is our drawings of whatever our hydrologic system are need to include the full atmosphere. And as we're setting up measurements and observations to test our perceptual models, we really, this is a sketch by Catherine Raphael at NOAA. We really need to work closely with both hydrologists and meteorologists to quantify the water fluxes and the energy fluxes through the temperature from space to the subsurface. I'm going to go on to questions, but if you have questions, I will just put up. These are just my opinions I give my students who are starting out modeling on what I think they should use to force their hydrologic model in the Western US. And you're welcome to ask me about it or not. I'll move on to questions.
Thank you so much, Jessica. We're opening the floor to questions.
Yeah, thank you very much, Jessica. The first things that we have received in the Q&A, it's a comment from Sophie Khan, and please confirm if this is for Dr. Longquist or for Dr. Goeking. I'm just going to read the comment for everyone. We are trying to model the recovery in the Sierra, but struggling to get it right. Remote sensing shows fast recovery of vegetation, which can be driven by the fact that greenness or LAI is the measure of recovery in remote sensing data. but our ecosystem model shows 10 to 20 years for full hydrologically relevant recovery. That is not necessarily same biomass, but vegetation recovered to a point where hydrologic change is it's not longer there.
Okay. Do you want me to comment on recovery in the Sierra, or do you want Sarah to? I can give you my opinion. I mean, I think you've got different plants growing, right? So the LAI, like once the trees go down, you grow a huge amount of, I call it shrubbery. Sarah probably calls it something better. And it's changing. And I think, I don't know what the word recovery truly means, but the hydrologic fluxes are going to be changing and in flux for 10 to 20 years. And the rooting depths, which Ying has done a lot of work on, really, really are relevant there. So I think we probably need multiple types of remote sensing data, and maybe more than greenness. I feel like the shrubbery often looks even greener than the trees when I walk around there. Sarah, you want to say something?
Sarah, you're welcome to speak up. You're muted.
Myself? There we go.
Okay, good.
Thank you. I was just typing in the Q&A everything Jessica just said. Shrubbery is great.
Okay, good.
Grasses and shrubs, a little different, but all of that, yes, great answer. And one of the things that you could use could be a height data set, spaceborne light.
Yeah, that's a good one.
Thank you both. Yeah, so the next question is from Jason Regina, which is asking, Dr. Longford's perceptual models seems to skew to longer timescales by default. An outstanding challenge in the field of operational hydrology is forecasting catchment responses to intensive convective scale precipitation events that may only affect a small town or village. Do we have perceptual models for regions subject to extreme hydrological processes that occur at shorter timescales, say days to minutes? Are these dragons?
I think we have a lot of different perceptual models for this. I like the terming these dragons, especially when you say they're convective precip, right? Because then there's thunder and lightning and it sounds like dragons. But I think, when I was putting this together, I actually, wanted to put together a lot of slides from Ken Bretman, who works for the U.S. Army Corps of Engineers up here and actually forecasts the inflow and takes control of all the dams and all of these floods. And he has a whole set of things he's looking at and thinking about. And I think that a lot of times the perceptual models of the forecasters who are used to this basin, used to this data, used to, forecasting for this particular town or this particular reservoir, that their knowledge is more important even than your typical official model, because you can adapt quicker in the moment and make decisions as the data come in. And a lot of it is that, during big storms, a lot of things break really quickly, and you need to have healthy skepticism to every data stream you're getting and say, wait, this one doesn't make sense, and change it. And you need to know your area and use all available information. But it's definitely, it's battling with dragons, I would say.
Thank you very much. So the next question is from Louder. Great talk, thanks. You focus heavily on precipitation and temperature data uncertainty. Do you think there is much to be gained working on model improvements, possibly through accounting for this uncertainty somehow in these regions? Or is that futile until we have better foreseeing data?
I think that's a really good question. And I think the number one thing I would recommend is I found a lot of particularly students I've worked with tend to think that whatever they get in terms of meteorology is truth, and they will tune everything else. And I think that is a big mistake, because you can often create really unnatural things in your hydrology model to try to compensate for incorrect meteorological data. I think really I feel like we as hydrologists want to have a stronger voice in the atmospheric science community, that their data matters to us, and we are often finding errors and issues with it that they are not aware of, because we are using it often in applications, they're not fully checking. So for example, if there's just not enough gauges and in a region, and those same gauges are what every meteorological model is tuned to, but they're wrong, and no hydrology matches it, we need to get back that, okay, your model should not be tracking these gauges. We need to make some differences here. So I think there also are cases wherein you have more certainty, and that's where I would work on the hydrology. But if you're tuning to match runoff without putting the correct water in, it's futile, might be the right word. But giving feedback, again, to fix the precip and temperature data. And I often tell my students, number one, just start presuming gauge under catch and multiplying precip by various numbers before you do anything else.
Thank you. Okay, we have 4 more minutes for the questions, and I'm seeing just one comment here and reading out loud from Ryan Webb. Great presentation, Jessica. Thanks for defining the difference between conceptual and perceptual models early on. I had been using the terms interchangeably, but now understand the difference. Yeah.
One with the dragon, one without.
That's what AI said.
Free to post if you have. We have time for one more question until the break. Sorry, Ying, you're muted.
Sorry, I have Jessica, I have a question for you. What's your advice in dealing with complex terrain? We are on large-scale models. We can't simply resolve every mountain path and every hill slope. So what is to be done? And so fundamental, so important. What can we do?
I mean, I think there's a couple things. One is that those, at least for the Western US, those storms that hit the mountains, I don't know if I have back to, I can't see anything on my screen here, but if I stop sharing, that in reality, the storms that bring the most water come from the Southwest. They're those really wet storms, and they tend to interact with the mountains in very similar ways. So actually, the locations that tend to get the most water are the same locations almost all the time. The locations that tend to get those cold air intrusions tend to be the same locations. To me, this makes mountain hydrology, if you have good training data, which I just sort of told you was not a great idea, but if you have good training data, it's actually really a good situation for machine learning or repeatable patterns. That there's a lot of downscaling you can do. That you can say, okay, when we get this bigger pattern thing, this translates to the smaller pattern thing on the landscape, which you can then represent statistically. I actually think there's, for a lot of the hydrology, right? You need to know, how much rain, how much snow, what was that dividing line very accurately. But then you can do a lot of lumping, right? In the winter, it's actually really wet. There's a lot of simplification that comes out of the mountains. And I feel like there's a lot of the downscaling is really statistically robust because the mountains exert such a strong control on what's going on that understanding the patterns resulting from the atmosphere interacting the mountains gives you a lot of guidance to your hydrology. You can do, the fact that the snow hangs out, you can do a lot of like data assimilation, remote sensing to update your snow before you do the rest. So if you can get through the flood season, Adrian will tell you in the next talk, like how to get through the snow melt season. And I think like that's actually where most of our forecast skill is. Despite snow being hard, we actually are able to do a lot of really good hydrologic forecasting based on knowing where the snow is.
Thank you. Julia, back to you.
Okay, thanks everyone. So we're going to pause here for a 5-minute break. I know this is a long morning session, so we're just going to hang out for about 5 minutes and then we'll be back at 11:35 Eastern. That's 8:35 Pacific. Okay. Thanks, everyone. We'll get started on the second portion of our morning.
Ying, you're muted, sorry.
Sorry about that. Our third speaker is Adrian Harpold, professor at University of Nevada in Reno, focusing on mountain eco-hydrology, which pretty much everything. But today he'll talk about snowpack dynamics, vegetation response, and the feedback, and how that feedback, that interaction shape the water balance, such as stream flow. So Adrian talk will focus on mountain hydrology, but from the angle of water balance resulting from the snow and vegetation feedbacks. Thank you, Adrian. The floor is yours.
Thank you, Ying. Does this look okay and you all can hear me? Great. Well, what a great panel to be associated with. Sarah and Jessica's work is so cool. And I saw Dave give a talk next week, so I actually kind of know what's coming from Dave. I'll try to set him up. I am going to focus this talk on snow, and I will argue that point in the next few slides of why that is critical. But what I want to sort of bring your attention to is the multiple scales which with snow variability occurs in the mountains of the West, and we might have to put into our perceptual models. Then I want to conclude the talk with a discussion about what this means for stream flow generation and the downstream processes of snowmelt. So Hillary McMillan has been doing really great work compiling a lot of the perceptual models existing on watershed hydrology, and snow becomes important. It's a little difficult to see here, but the green color in the center here is snow. So snow is in a lot of these, but when you look across these perceptual models, most of them have a relatively low snow fraction. And some previous work has excluded areas with higher snow fraction. And I'll explain why I think this is on the next slide. But if you do that, you basically leave out the entire Mountain West. So most of the Mountain West has snow fractions greater than 30%. Why might you leave out snowmelt when you're looking at streamflow generation? It's because snowmelt has such a dominant role on streamflow generation. And Jessica set this up a little bit. But this red highlighted area on the hydrograph from Sage-Hen Creek near me in the Sierra Nevadas shows the classic spring freshet, the snowmelt freshet that sets the stage for basically the entire stream flow annual and seasonal cycles. A nice paper a few years ago tried to model how much of the stream flow results from snowmelt, and the leftmost panel being in the historical and the right two panels being out into the future. So if you look in the historical, you're looking at 50+% of the stream flow being derived from snowmelt in most Western US basins, especially the ones, as Sarah mentioned, that are really important for our water resources. Here's another way to think about the importance of snow for stream flow. What happens when you get a lack of snow or a snow drought? So this is a figure from an EOS paper we published a number of years ago. I want to draw your attention to the right side, which is the stream flow from a creek in Oregon and a creek, the bottom panel is a creek in the Sierra Nevada near me. The red line is this drought year in 2015, and you see just a very drastic deviation from the normal long-term average, the dotted black line in stream flow, where you get earlier stream flow, more episodic stream flow peaks, and a smaller volume and amount of stream flow in these snow drought years. So snow really sets the template of stream flow response in the Intermountain West and most of the Western US. So I want to present this dichotomy of challenges we have, which is that we have effective ways to predict snow melt and snow distribution right now. We've done it for a number of decades. As Jessica mentioned, it's probably one of the more skillful parts of some of these models. And so we have some real tools to do that. But we also have some real challenges in this areas. A lot of our model, we don't have a model that we all agrees works really well. So we still are spread across many models. We really struggle with bad precipitation estimates, which was discussed. And the snowpack energy budget is very complicated, as is rain on snow and movement of liquid water through the snowpack. So there's some real challenging processes at hand. I think the question is, which of these do we need to include in our perceptual models? So what I'm going to do is I'm going to take us from sort of a regional scale down to a basin watershed, and then the stand scale, sort of the hill slope level scale. So starting at a regional scale, we really have these drivers of climatology as our main drivers of snow variability. So this work by Ernesto Trujillo and NOAA Cooperative took all the snow tells from across the Western US. They estimated these things about the length of the snow season, the peak snow water equivalent, and they built these long-term sort of climatological snow relationships. And so I'm going to show these relatively quickly just to give you a sense of the big broad patterns across the West. If you look sort of north to south across the Rockies, you can see that the accumulation season is longer, and then in the sort of middle northern Rockies and the southern Rockies, we have latitudinal gradients. If you look more east to west across the Sierra Nevada to the Basin Range to the Rocky Mountains, we have big humidity and precipitation gradients that drive different lengths of the snow season relative to their peak snow water equivalent. So there's variability driven by climatology. Ernesto did something similar for the ablation or the mass loss of snowpack. And so you see similar latitudinal gradients in the middle to southern Rockies, where the snow melts generally slower in the northern latitudes. And then gradients from west to east here showing that the ablation generally happens faster in the Sierra Nevada relative to the Rocky Mountains. The reason that this generally has to do with solar radiation. One thing that we're pretty good at modeling and measuring to some capacity is solar radiation. And we're able to show these very strong relationships between how much solar radiation occurs in the spring and the timing of that, and the timing of spring melt. So earlier snow melt occurs during periods with lower solar radiation. And we can extend that relationship in the right-hand panel to think about the effects of solar radiation on spring melt. And this shows that earlier spring melt leads to lower solar radiation and slower melt rates. So counterintuitively, this relationship driven by solar radiation actually leads to earlier and slower snow melt under warmer conditions. And we see this relationship over the last 40 years in the empirical data. We see slower one-day maximum snowmelt rates and slower spring snowmelt rates. So this perceptual understanding of why spring snowmelt rates would slow seems to be borne out with the data set that we have, although it's very difficult to measure some of the causality here. We can look at another ablation time period. So instead of looking after peaks at the spring snow melt rate, we can look at the winter melt. And the winter melt is interesting because it's water that is priming the soil, but possibly not contributing to stream flow in the spring like it would if it melted in the spring. And when we look at winter snowmelt, we see quite a bit different relationships. So we see more winter snowmelt, and we see a real geographic regional patterns where that impact is most up in the Pacific Northwest. So in a paper in 2018, Paul Brooks and I pulled this relationship apart using some gridded data because that was the best available. And we were able to show, I think, pretty compellingly that the humidity regime at these regional scales is a big driver of winter snowmelt. So in places that have more winter humidity, you see more snowmelt for the same temperature. And so this is how you can get relationships where snow melts relatively efficiently in higher humidity places like the Cascades, but persists longer in lower humidity places like New Mexico and Arizona. So I'm going to bring us down from that large regional and basin scale down to the stand and watershed scale. So now we're going to think about more complex terrain and issues related to the land surface. And I don't have the time or real capacity to go into the snow energy budget, but at this scale, we have a lot of influences on the snowpack energy budget that affect snow distributions. So when we go down to the watershed scale, topography becomes really important. As was mentioned previously, we see very repeatable patterns that are driven by repeatable precipitation patterns, snowfall patterns. So this data is collected by LIDAR out of an airplane over the Sage-Hen Creek watershed here nearby in the Sierra Nevada. And what I'm showing on the right-hand panel is grouping that data into snow water equivalents and elevation bands and aspect bands across two different periods, one in 2008, one in 2022. And what you see is repeatable patterns, more snow at higher elevations, but less snow in south-facing aspects than north-facing aspects. In fact, if you look across these red box and whiskers, you see about the same amount of variability you see across just the lower elevation across the different aspects. So you have aspect and topography controls that have been widely shown, but we now can show them with LIDAR. Zooming in even one step tighter, we start to see the effects of land cover, especially vegetation canopy, on the snowpack. So this expresses itself as wind, sheltering, and redistribution of snowpack, shading of the snowpack. The forest itself gets warm, emits long wave radiation, and the snowpack also intercepts snow. So to give you a sense of the challenges that this presents from a modeling standpoint, I'm showing a paper from Jessica's work a number of years ago where she looked across some empirical studies across the globe showing that snow disappeared quickly, it ablated more under the canopy in warmer climates, but in the open in colder climates. So we get this trade-off between long and shortwave radiation that actually depends on the local climate, but expresses itself at the tree to stand scale. Some work by a PhD student, Hamadeh Safa, tried to look at this relationship, but across elevation, aspect, vegetation, and site controls by combining LIDAR data sets. And what we see is generally what Jessica saw, which is these circles are the the under canopy areas have more snow in this warmer site in the top panel, and the open sites have more snow in the colder site in Colorado. But when we look across elevation and aspect and vegetation controls, we get a much more complicated picture. So we developed a perceptual, maybe conceptual model in this paper that Hamadeh published in Water Resources Research, where we thought about how not only climate, but aspect, elevation, and vegetation density affected this relationship. My last example here is the effects of wind. So a current PhD student, Eli Boardman, is working in the Wind Rivers, which you can imagine is a windy place, also very snowy. Wind has dramatic influences in many mountain ranges. We really struggle to capture it in a lot of our models. And Eli is actually demonstrating that the spatial heterogeneity of the snowpack is a major driver of stream flow, low flows, and water resource management in this area of the Wind Rivers. So I spent some time putting some thoughts together about snow change in the mountains, which isn't exactly this talk, but there are these key processes that we need to capture in our immediate climate, but also thinking about into the future. Those have to do with regional climatology, basin scale weather events and topography, watershed scale topography and interactions with wind and weather, and then this stand scale forest structure and fine scale heterogeneity. From this, I'm going to pivot the last part of the talk here and think about what this means for stream flow generation and stream flow change. So another amazing PhD student I had the pleasure of working with was B. Gordon, and she published a paper in Environmental Research Letters, which wasn't exactly the point of this talk, but it was thinking about how snow change will be expressed as stream flow, because we know snow is going to change in the future under climate change. So the perceptual model that we came up with there, we have three mechanisms by which we think local watershed basin scales will respond and maybe respond unevenly. And I'll go through these quickly to wrap up my talk here. The first one is snow season water vapor fluxes. And the simplest way to think about this is primarily driven by a snow albedo feedback from a shorter and sparser snow season. And some work by Milley et al. In Science in the Colorado River Basin really made the conclusion that this albedo feedback was the driver of declining discharge in the Colorado River Basin. So capturing this process and constraining changes in the snow season water vapor fluxes, both abiotic and biotic, as Sarah mentioned, I think is a big challenge. This is a recent paper by Jessica showing or arguing that these spring storms that bring in both cloudy weather and fresh snow that changes the albedo really reduce the evapotranspiration demand. And that effect of winter precipitation combined with the reductions in evaporative demand is a reason that we see variability in runoff efficiency in the Colorado River Basin. So this question of changes in snow season water vapor fluxes, I think, remains open and a challenging modeling paradigm. The second point, the second mechanism is a change in the intensity of liquid water inputs. This wasn't mentioned exactly, but as we shift from a more seasonal snow cover to more rain and ephemeral snow melt, so melt through the winter, we are increasing our short duration intensity of precipitation or effective precipitation. So over the scales of like 1 day, we're getting more intense precipitation, effective precipitation, but over longer durations where snowpack really acts, we're getting decreases in intensity. And these examples on the right-hand side are soil moisture responses from a seasonal snowpack versus an ephemeral snowpack, and the dynamics just are visibly much, much different. There's quite a bit of good evidence that the seasonal release of snowmelt is an effective driver of groundwater recharge. So connecting this change in intensity to routing and storage in the subsurface is a big challenge. Then the third mechanism is the synchrony of energy and water. So we expect water energy to increase in the future under climate change, water demand decrease in the future, but this shift in timing of water inputs from more rain, more winter melt is going to change the synchrony. We know that when water comes in at low energy times of year, it's more efficient at generating stream flow and groundwater recharge. So nice work by Rosemary Carroll demonstrates a sort of different version of that, where The spring snowmelt is a much more efficient generator of stream flow and groundwater recharge than the warm season summer monsoons. We need to think about the synchrony of precipitation and evaporative demand in our models. Okay, so my last slide, my wrap up here is that we need to capture snow and precipitation to get the right answers for the right reasons. I think that is a little bit redundant with what Jessica was saying, but I'm bringing the snow into this. Snow varies across these scales, and which of these processes we want to or need to include, I think, remains a bit of an open question. And how the snow melt cascades through a hydrologic model into subsurface storage and routing remains a real challenge for the community. We don't have a lot of observations. We don't often really treat the vegetation as thoroughly as we should. And we don't think about the sponge of the subsurface probably like we should. So with that, I will take questions and start a discussion.
Thank you, Adrian. We are opening the floor for questions.
Thank you very much, Adrian. Great presentation. So I'll read the first questions that we have from Arsh Garwal. This is a question for both you and perhaps for Jessica as well. It seems to me that snow is much more difficult to model and measure during the accumulation phase compared to melt. Is there a valid case for shifting our focus into measuring peak SWE directly? Should we shift our resources into more snow surveys, snow pillows, and remote sensing techniques to capture peak SWE instead of trying to measure or model snowfall and snow redistribution?
I can start, and I'm sure Jessica has some thoughts. I think peak SWE is a very useful variable in a lot of ways. If you don't have melt or other losses ahead of peak SWE, then that captures a lot of information about precipitation. But I think that's actually very unusual, and typically there is ablation before peak SWE. And so you really end up wondering, you know, what you don't see, was it there or not? And you still lack that information. I was making the case to the Airborne Snow Observatory that flying before and after individual events and measuring the change in snowpack over individual events would probably be a good proxy for precipitation. But I'll let Jessica weigh in on that as well.
I think some sort of data assimilation at peak SWE for the rest of the runoff season is a really great idea. Whether you're using ASO data, remote sensing data, I mean, I think, yeah, it's not either or, but an and. As much as we can do, I would update your hydrologic model near peak SWE.
The next question is from Wouter. Nice talk, thanks. In one of your earliest slides, you talked about winter melt events, priming the soil for spring runoff, but not contributing much to flow at the time. Can you talk a bit about the processes that control, sorry, it is going up as people are posting questions. Can you talk a bit about the processes that control that? For example, lack of infiltration due to frozen soil.
Yeah, that's a great question. I don't think about frozen soil much. That's more of a more northern problem than I usually think about. But I mean, it has to do with the capacity of the soil to take that water, which is both frozen, the infiltration rates, all of that, but also what the summer and fall look like. Did you get a big rainstorm prior to the snowpack accumulating? It has to do with the intensity by which those winter melt rates are occurring. They tend to be low intensity events, but as Jessica said, that we also get these big rain events. We get our big flood events in the winter in some of these places as well. So that's a bit of a different mechanism. I think that we have some observations of that, but modeling how much that priming of the soil matters, I think, is an open question. I know Dave will talk a little bit about that.
Sure, yeah, great. Our next question is from Martin Clark. Adrian, great talk. Given the rapid changes in the cryosphere that you mentioned, should we still be calibrating hydrologic models over a historical time period to forecast stream flow in the current era? Can you comment on how changes in the cryosphere affect our approach to operational hydrology?
It's a great question. I think if you're using a very simple empirical model that relates the past to the future in sort of a regression type of way, I think we do need to start to wonder if we can really look as the past for a proxy for the future. I do think that when we are trying to build confidence in our future predictions of cryosphere change, process-based models have to be a player there, because I think they give us confidence in ways that more machine learning or black box models would not. I think maybe instead of looking to a Nash-Sutcliffe efficiency that matches the daily SWE, we might really start to challenge our models in more dramatic ways, where we ask them to predict more extreme events or more extreme conditions. But I do think we need to use validation of the past as a way to give confidence for future predictions.
Thank you. And another question is coming from Arsh Gurwal. You mentioned getting the right answer for the right reasons. Should we make a push for collecting good tracer data, such as stable water isotope, for snow, which is very rare, to constrain our hydrologic models?
I mean, I think the answer is yes, but what exactly is it? I mean, it's not the real forum to get into a discussion about stable water isotopes, but what a mess in snowmelt systems. They're just so hard to know what the inputs are and the variability and all of that. So I think the answer is yes, but because there's no tools that really give us, all the insights we want, we need a whole toolbox of different tools that we can apply. But I do think, was it Mike Dettinger or somebody recently made the case, other communities like the oceanographic community is able to go out and really make a case for big observational networks. The hydrology community maybe hasn't done as well with that, but I do think there are some key observational needs and a lot of value there.
And we have a questions from Sarah Goeking. Great presentation and summary of where to improve models. What vegetation data sets do you think are most promising for improved operational modeling of snow? And are there circumstances where it becomes more critical to use those inputs other than land cover types?
Oh, what a great question. I mean, here's my opinion. I think our models are just at the nascent stage of including vegetation in this capacity. My soapbox recently has been like, none of the operational models even have, these landscape scale fire events in them. So we're basically running our forecasting models, pretending like the biggest fires in, the last several thousand years didn't occur. So I think there's really low-hanging fruit for just representing disturbance and representing variation like that. In terms of the more process pieces of the models, it's probably worth a longer discussion. I mean, snow interception is obviously very related to the talk, but what I found working with these models is that depending on the model, how it's conceptualized and the math is written, the different parameters are more or less sensitive in different models. But what I found is that hydrology models are very, very sensitive to anything leaf area index. So anything related to scaling leaf area seems to be a huge issue, a huge sensitivity for the hydrology models.
Okay, we still have 6 or 7 minutes for questions. but we haven't received any new questions yet. So please feel free, if you have more questions, post it in the Q&A.
While we're waiting for more questions, I have a question for Adrian. You showed a slide of the wind redistribution of snow. The scales are meters. What do we do?
Well, I think it's actually even worse than that, because the scales are kilometers to meters. You know, it's sort of like this whole multi-scale thing that I was mentioning. So Eli's work in the wind is showing, in the wind rivers, is showing that wind pushes snow over the basin divides, so into other watersheds across sort of like topography, like hill slopes, and then down into these little drifts that, to your point, are on the scale of meters. What do we do? Man, this one is really tricky. Again, I think Jessica's point about repeatable patterns is really, this one is very much that. I think there's a lot one could learn from the repeatable patterns and sort of empiricizing that into the models. This is definitely, again, one where we have to reach out to the atmospheric community. I know that Ethan Gutman has developed this like mid-moderate level complexity, effectively WRF, and something like that, you could actually resolve some of the turbulent fields and some of this. But yeah, I think the winds in the mountains remains a real challenge for our models.
Thank you, Adrian. So here's another question coming from Gordon Brandt. Nice talk all around. Adrian, your talk, along with the others, emphasizes the role and importance of the sequence of climatic or precipitation events in determining stream flow. Where do you think the modeling community is with respect to acknowledging the role of sequence and building statistics accordingly?
Ooh, that's a good one. That's a good one. Yeah, I mean, and it's another one of these multi-scale problems, because you have, you know, memory that occurs on sort of the daily to hourly scale in terms of priming a watershed for a big flood event. But then you have memory that occurs on the year to decadal scales that is related often to groundwater and rock moisture. And Dave has some good examples on that coming next. I mean, the process-based models get the sequencing of events sort of implicitly if the time step is resolved enough. But thinking about what that means in terms of the accuracy of our predictions, I think is an interesting one. I mean, another soapbox I've been getting on recently is just the lack of our ability to benchmark snow models, meaning tell ourselves and the community how accurate they are relative to reality, but also relative to each other. So one could imagine, you know, thinking about the role that like the sequencing of weather events or something like that might play in the accuracy of our models. But I do think the benchmarking piece to really even answer the question of how much does the sequencing matter and where our models fail or don't remains a challenge. We need better validation and benchmarking.
Zero, great points. Yeah. So the next question is coming from David Drally, and the question is, what do we know about lateral transport of water fluxes in snowpack? Can we just say that meltwater infiltrates vertically in the subsurface, or do we need to be thinking more about how snowpack might shortcut melt fluxes straight into the stream? Circumventing the need to store that flux before discharging it.
I mean, anybody that's sort of done the classic dye tracing experiment as a snowpack where you put dye on top and you watch how it moves through. I mean, it is a very heterogeneous media. In my experience, the longer sort of seasonal melting, you probably can get away with more vertical assumptions that the pack melts directly down to the soil below it. The more intense and the shorter duration events like rain on snow, I think that's where the evidence, especially, you know, when you put these on some kind of steeper topography, get a gravity head, that there is quite a bit of evidence that water does move down laterally on the hill slopes. You know, probably what we end up doing is parameterizing other parts of the models to capture that quick response because we don't have that lateral conductivity in our snowmelt models. Yeah, so I don't know if that's exactly answering the question, but yeah, I do think that's a challenge at shorter timescales in particular.
Great. And the last question is from Safi Khan. Can you speak to the snow vegetation interaction from the perspective of snow being a major source of ET during dry season in Mediterranean climate? How changing snow will accelerate vegetation disturbance, especially in places where subsurface storage is limited?
Yeah, so we have done quite a bit with looking at disturbance effects on vegetation disturbance effects on snowpack. We see maybe, I don't know, ballparking like a 10 or 20% increase in snowpack. When we put that through our best guess hydrology models, those numbers almost always go down to like more like 5 to 10%. So meaning that the vegetation or other sort of warm season vapor losses are compensating for some of that increase in snowpack. I'm not sure I fully understand but the second part of the question, but I do think the feedbacks between vegetation growth, dead and live fuel moisture, and then feedbacks to more disturbance, those are things that aren't well understood. And really, I think the collaborations with like the forest ecology community that really predicts, you know, vegetation succession and things like that probably need to be stronger if we want to predict some of that.
So much. And we address almost all of the questions that we have received. Thanks, everyone. Ying, back to you.
Okay, thank you, everyone. And our next speaker is David Drawley. David is a research hydrologist at U.S. Forest Service, like Sarah wasn't. Sorry about that earlier. And David is one of the young leaders looking, really probing deep into the subsurface, and particularly the use of rock moisture, which is a far greater storage than the thin soil in the mountain terrain. And there are several very insightful papers that came out from David and colleagues. And so we're going to hear more about that today. So David will now talking about the mountain hydrology now entirely from different angle, from the subsurface, very opaque subsurface angle, and how they really hold the key to a lot of what we see on the surface expressed by vegetation, for example. And David, the floor is yours.
Thanks, Ying. I appreciate that intro. And thanks, Adrian, for making some subtle references to what was coming next. I appreciate your teeing this talk up. Thanks to my collaborators, especially Dana and Jesse and Daniela, who Ying referred to are, you know, as much responsible for this work, if not more than me. So I'm here to represent this group of people. And I'll motivate this talk by just saying that mountains worldwide are changing, especially true in California. I said this last week at a talk that Adrian was at, that you can throw a rock in California and hit a hydroclimatic extreme. We've gone from the driest years on record in 2017, or rather in 2012 to 2015 during the historic drought, to some of our wettest years on record in 2017, narrowly avoiding a disaster at the Oroville Spillway. And recent droughts, like I had mentioned, have really shown that all kinds of our predictive models are lacking. We can't fully predict tree mortality, for example, from soil or climatic factors alone. And in 2021, the Department of Water Resources flow forecast massively over-predicted snowmelt runoff coming off of the Sierra. So a big question is what's missing in some of our models that might explain some of these patterns. And I'll just say or acknowledge that the answer to this question is very complicated. Proximate causes of mortality, like pests, for example, are not particularly well understood. However, there's a fundamental yet sparsely or incompletely documented variable that sets the stage for eco-hydrological response to drought, and that's subsurface water availability. Whether or not climatic drought results in eco-hydrological drought is really a question of weathering, not the weather, but weathering profiles. That is the layers beneath the surface where rocks gradually break down into smaller particles over time due to chemical, physical, and biological processes. And weathering profiles, an archetypal one I've pictured here with subsurface structure and corresponding water storage elements, are not monolithic things. They're, as they are often conceived of in eco-hydrological models. Instead, subsurface weathering profiles transition from typically really thin soils at the surface to weathered fractured bedrock beneath, typically within a meter or two of the soils or within a meter or two of the surface. And then finally, tens of meters below the surface, we commonly find layers of fresh bedrock, which is still solid and largely unaffected by weathering. And I like to say this a lot, plants and streams don't care how much it rains or snows per se, they care how much water is stored in these weathering profiles. In our winter wet, summer dry Western climate, trees have to dig deep for water, typically way beyond thin upland soils into the weathered fractured bedrock beneath, where plant available water is stored in unsaturated moisture held in rock, and where stream-based flows originate from saturated fractured rock aquifers, sometimes tens of meters below the surface. And it's these deeper storage dynamics that I want to highlight today, and in particular, how weathering and rock are important for understanding hydrological behavior in mountains, and some ways that we developed to bring new information into our models and quantify some of these storages at scales that matter for management. So to illustrate the importance of weathering profile structure and water storage dynamics, I'll begin with a natural experiment that first presented to us as a sort of ecological mystery. Here we are along the north coast of California in Mendocino County, and what we see is an ecotone as we move from west to east, from dense forest in the west to oak savanna. This is not explained by climatic factors or anthropogenic factors like land use. Instead, things only seem to come into focus when we overlay a geological map on which we see that this ecotone aligns with the boundary between two belts of the Franciscan Formation, a geological complex in Northern California. On one side, the coastal belt of the Franciscan features a thick shale sandstone weathering profile that stores large volumes of water, supporting dense forests and robust summer base flows. And to the east, the central belt has a thin weathering profile with impermeable clay-like material just a couple of meters below the surface, which results in rapid filling of the subsurface upon the arrival of wet season rainfall and more runoff and less water for trees and streams during the subsequent dry season. And I'm not going to go through everything in this picture or much at all, but I'll just say that this is a conceptual summary largely put together by Jesse Hom, just illustrating how rock type impacts both subsurface structure, but also it controls water storage, where it's stored in the subsurface, the sort of energetic phase of the water, whether it's stored in the unsaturated zone of the groundwater, and ultimately runoff generation and flow paths. And these different weathering profiles have very different consequences for runoff generation. So these are hydrographs from our two experimental watersheds in these two lithologies. And generally speaking, there's a couple of cool findings that pop out that I'll talk more about here in a second. We find that large plant-driven water storage deficits in soil and weathered bedrock in the coastal belt watersheds result in slower activation of streams at the start of the wet season, as pictured or as kind of quantified in this upper left plot, where I plotted some metric of storage on the x-axis and discharge on the y-axis, just really showing how you have a much more rapid activation of flows in these small storage catchments that you find in the central belt. as compared to the slower activation and more kind of buffered and smooth flows that you find in the coastal belt catchments to the west. And I've been talking about hill slopes and some of these catchment scale studies that come out of my group, but I'll just mention that the larger Eel River watershed in Northern California is really a geological hybrid consisting of subwatersheds of varying geological composition. So here we see some gauge watersheds mapped across the Eel with flow behaviors as a function of the fraction of contributing area underlain by central belt melange geology. Again, that small water storage geology. We see a smooth gradational response of flow recession timescales, that is the rate of drainage of stream flows after precip, from slow in the coastal belt to rapid in the central belt, with kind of smooth variation between those percent compositions. And I think this really points out something important, which is that watersheds are really just collections of hill slopes. And so this is evidence that hill slope scale understandings and storage dynamics can be used to extrapolate and explain watershed scale behaviors. Something important I want to note is that if we had not looked deeper into the weather bedrock, we would not have been able to attribute these differences in seasonal water storage to subsurface factors. So shown here is the typical off-the-shelf plant distributed plant available water storage capacity from the CIROH soils data set. These maps can be accurate, but they're limiting to describing just near surface soils. In many watersheds, we need to go deeper to really explain the differences in storage, runoff, and evapotranspiration that we see in real mountain landscapes. As we've shown, or as I've discussed, this root zone water storage capacity variable is really an essential one for understanding water budgets in forests. This is especially true in seasonally dry climates, where the subsurface is really kind of a middleman that stores water, rather precipitation and snow that arrives during the wet season, and then subsequently making it available to streams and trees over the long months of the dry season. So hopefully I don't offend too many of the more complex modelers and hydrologists in the room, but to understand why root zone water storage capacity is so important, I want to rely on a really simple but surprisingly accurate physical analog, the wetting and drying of a kitchen sponge. And I'll say at nearly every site where we've directly observed subsurface flow paths and storage, this sponge physics that I'll describe is really how root zone water storage appears to work, and consequently how runoff generation processes proceed upon the arrival of precipitation. So the first kind of point is that those of you who have cleaned dishes are familiar with the fact that a sponge can be it can soak up water to a capacity. Any additional water that you add to the sponge after reaching that capacity drips from the sponge. And this drip is really can be thought of as the recharge to the groundwater systems in our streams. And again, in mountain environments, groundwater largely is the primary driver of stream flow. The ultimate or the original source may be rainfall or snowpack or whatever, but really it's groundwater systems that mediate the runoff process. Once the sponge stops dripping after you've turned off the tap, it nevertheless remains wet. There's no physical mechanism of squeezing and drying in the subsurface. It's really only evapotranspiration that fully dries the sponge. And so to summarize the metaphor, our sponge really and the sponge size dictates two essential features in my mind for modeling and understanding forest hydrology. And it's that the sponge size dictates the plant available water storage capacity. So what is the total amount of water that can be stored, the potential in a watershed for plants. It also, that sponge size and the extent to which it dries dictates how much precipitation is needed to generate flows. And sponge dynamics underlie the models that we use to parameterize ET and loss from the root zone in many of our hydrology models. So here are two famous examples, the FETIS model, where this sink term, you can really just look at this plot, this S on the vertical axis. I'm realizing that might be conflated with storage, but it's not. It's meant to be interpreted as a sink or an ET, where we see loss as a function of storage and other factors that aren't plotted here, like potential evapotranspiration. And a more recent model from Lyo et al. in 2001, really with essentially the same shape, but also pulling in some other soil parameters like saturated hydraulic conductivity. And as I've mentioned, these physics, sponge physics, the models I just showed you seem appropriate. But a major challenge is how do we observe and parameterize the sponge in deeply weathered catchments where bedrock really does matter? These storage elements and these deeper compartments of watersheds are cryptic and difficult to observe, as evidenced by the frequently labor and time-intensive tools from geophysics and hydrology that we use in our site-based research. So a big outstanding question is how can we estimate key water storage properties of landscapes at scales that matter to national forests? And what can some of these estimates tell us about forest and stream resilience to drought? So one way we've addressed this observational challenge is to use rapidly advancing remotely sensed precipitation and evapotranspiration data sets, which we've already talked about are problematic in some ways, but in other contexts are the best we have, to track what we're calling a root zone water storage deficit. And a deficit is really just an inferential measure of how dry the subsurface sponge is. And you can think about this deficit really kind of an analog is a credit card balance. Withdrawals from the account through time, tree transpiration, versus deposits like precipitation or snowmelt tell us at any given time how dry is the sponge, and the max observed water storage deficit over some period of record places some lower bound on what the root zone water storage capacity is. And so once we have a deficit data set like this, what are some things that we can do with it? Well, it turns out that bedrock water storage isn't just a backup plan for extreme droughts for vegetation. Recent research, or a lot of research, kind of going back to the 70s to some extent, but I'd say the results are kind of more prolific and geographically distributed nowadays, has shown us that in many years, in most years, in a lot of upland, especially seasonally dry forest, rock moisture, water stored in bedrock is an essential and regularly accessed component of the root zone sponge. And in a 2021 paper, our collaborator, Erica McCormick, we assumed that root zone water storage is really just represented by the sum of soil and bedrock water storage, and then use this deficit data set, the maximum observed deficit over a period of record, to estimate with simple algebra how big must the bedrock water storage sponge be. And the findings in California were striking. Almost without exception, upland forested parts of the state we showed rely on bedrock water storage every year, as indicated by green in this map. And you know, this conference or talk, this series is about kind of regional perceptual models. These effects, this deeper bedrock storage, seems to be less of an important factor, which you might expect as you move east, where precipitation is more frequent, and perhaps vegetation don't have to go as deep to access water for evapotranspiration. And I'll say we've done more than just quantify deficits using remote sense data sets. For example, with our collaborator, Dana Lapidus, we used deficits calculated via these remote sensing methods to directly parameterize root zone water storage capacity in the LPJ-GESS dynamic global vegetation model, with big model improvements in seasonally dry watersheds. As I've pictured here in the upper left with the Elder Creek site, which is the coastal belt large storage watershed that I talked about earlier, where blue is the kind of default annual transpiration time series that we see coming out of that model using soils data sets. And then the red is the transpiration time series that we obtained after updating the model and including some new hydrology and parameterizing it directly using the deficit data set. This is compared to the ground truth or the actual evapotranspiration time series. I know we can quibble about ET time series, remotely sensed ET, and there are definitely problems there, but we seem to be more closely approximating reality, at least as represented by the ET data set with the red curve versus the blue curve. Recalling the sponge metaphor, I'll say that deficit dynamics are relevant to more than just plants. A really nice paper in 1978 notes that recharge is commonly calculated as the remainder when losses identified in the form of runoff and evaporation have been deducted from precipitation. And the term evaporation here in their worldview envelops transpiration. And this, again, this idea emerges in these simple loss models that I described earlier, again, with the LIO model in the bottom right, showing essentially deep drainage or drainage losses from the root zone into the groundwater above this soil field capacity, the SFC term along the x-axis. So to explore how deficits might affect runoff, I want to shift away from our coastal catchments to demonstrate how the ideas we just reviewed can help solve a large-scale water supply forecasting mystery in the Sierra. In spring of 2021, snowpack across the Sierra was below average, but not catastrophic on April 1st. Yet, subsequent spring runoff into reservoirs was historically low. It was so bad that the chief snow and water supply forecaster with California DWR, Sean de Guzman, noted we have 100 years of data saying if you have this much snow, you expect this much runoff. But that fell apart this year. So what happened? Let's start with a forecasting model of the form that failed us in 2021, a simple regression of spring runoff on snowpack and winter precipitation. Checking my time here. In many ways, this model is great. I've never been a huge fan of big, bad hydrological models. You have to pay millions of dollars to parameterize things that maybe you can't ever measure in the first place. But you can see how big of a miss this simpler modeling approach gave us in 2021, with that red dot kind of depicted on the bottom of that plot showing the forecast in the dashed line and the actual runoff observed in the red dot. The forecast was really more than twice as much water was predicted as we actually saw coming into reservoirs. And so we took a crack at a middle of the road approach. And I won't get into the nitty-gritty, but we created a mass balance model that only used observational and remote sensing data to predict spring snowmelt. Instead of a simple regression, we were able to break the model up to include major predictors that we think matter, such as spring evapotranspiration, melt rate, and groundwater recharge during the winter. And we wanted to try to attribute the missing runoff, the residuals in that model, to various potential factors. And importantly, we added a new predictor not present in the existing forecast model, the root zone deficit, i.e. the sponge. And remember our general lesson about how the sponge size impacts runoff generation. Basically, we fill it up to capacity and we get significant runoff. So what are some takeaways from this model, including the new deficit term? Here I'm showing you a plot of how important each term is for explaining the quote missing runoff following a wet year. The Nash-Sutcliffe efficiency, a measure of model accuracy, is really how good the model is. A 1 is perfect. 0 means that your model is no better than just having used the mean as a predictor. And in wet years, we see that this deficit term is not particularly important for explaining the additional residuals in the model. In fact, spring snowmelt or spring ET seems to be the big factor in kind of fixing some of those residuals. Things are way different in a dry year, though, i.e. emerging from drought like in 2021. In dry years, water use extends much deeper than soils data sets can explain. This implies trees are using significant amounts of bedrock water. Only the deficit that we incorporated into the study can really capture this effect, and it's far and away the most important predictor in the runoff model. So the answer to this mystery in this case is that deep drying fronts below soil in weathered bedrock slurped up some of the missing runoff. And the important take home for me is that the deficit can massively improve runoff forecasts following drought years. Okay, so with this new deficit product incorporated into runoff forecasting, have we kind of solved a lot of the issues, especially in some of the dry years with runoff forecasting? And the answer is not really. In some cases, we've had great success, but problems with the deficit that I want to walk through here really identify for me some compelling research questions that need answering. So I told you that hill slopes are important, yet the scale of much of the data that I've been presenting is much more coarse than the scale of most hill slopes. So for example, here's a PML evapotranspiration pixel laid over our experimental hill slope. really just illustrating that the pixel scale of evapotranspiration data sets is on par with the the entire hill slope picture that I just outlined. So a question is, how could subpixel deficit dynamics impact runoff modeling? Recently, we extended a method by Jim Kirshner using storage discharge functions to infer groundwater recharge. I won't go into the method, but I'll just say we can produce these time series of groundwater recharge as a function of time using the method. And so we see precip, we see recharge, and we see stream flow in this plot. And the deficit model would predict that this recharge time series is simply the excess of precipitation beyond the storage capacity of a hill slope. This would result in threshold response of runoff efficiency, with the fraction of precip getting converted into recharge going to 1 as the deficit is reached capacity or has been replenished. However, when we plot cumulative recharge as a function of precipitation at the start of the wet season, and we take a derivative, we see that this recharge efficiency term is not threshold. Instead, we see a smooth gradational increase with cumulative precipitation. We attribute this kind of effect to subpixel heterogeneity in the deficit itself. We've seen this at our site with direct measurements of the deficit using neutron probe, which appear to vary along hill slopes, with maximum water storage deficits near the ridge and minimum water storage deficits near channels. When we look at individual groundwater wells underlying these deficits or underlying these vadose zone water storage deficits, we recover this threshold response that we might expect, with recharge first occurring at the base of the hill slope and marching upslope as precipitation accumulates. The result is a kind of partial area effect in watershed runoff generation, with lower slope positions activating first and producing recharge and runoff before the higher upslope positions. Another example, the deficit model that I just described as formulated is one-dimensional. However, we know that lateral groundwater fluxes may subsidize evapotranspiration, as hinted by DL oscillations in base flow, pictured here again in the Elder Creek catchment that I discussed earlier. A question is, does the deficit have anything to offer here if it kind of fails at representing some of these potential lateral sources for ET? We return again to our finding that deficits vary along the hill slope. Supposing that, just for the sake of argument, ET is homogeneous along a slope, this would imply that vegetation water use of groundwater increases downslope. So if deficits in the vadose zone are larger at the ridge and smaller at the channel, yet total ET is constant, we would predict a sort of higher dependence of vegetation on groundwater as you move closer to the channel. This is not a study that we've completed, or I can't cite a paper here, but it's really just kind of a more generic point about how deficits might fail, but how investigating them more closely at the scale of hill slopes might reveal some dynamics in terms of plant water use and access that we've not really incorporated into models yet. Okay, so just to wrap up, some of the take-homes are that ridge zone water storage deficits we've found are a really powerful but limited organizing concept for understanding and predicting how streams and trees respond to drought. The whole weathering profile, including soil and bedrock, is required to explain water storage deficit magnitudes, especially in our seasonally dry Western climates, and most especially in California. And finally, half of our forest is underground. So we need to dig deeper and peer inside of hill slopes to understand how deficits and water storage dynamics in the deep subsurface impact runoff and water stress. Thanks to the organizers and everyone for listening. I'm happy to hang out and take questions.
Thank you, David. That's fantastic. The floor is open for questions.
Great presentation. Thanks, Dave. And our first questions here is from Jason Regina. Dr. Durali, the sponge metaphor is useful. What about subsurface flow when the sponge isn't at capacity? It has been over 10 years since Bevan and Grimond published their macropores revised paper. What challenges need to be addressed to create models, such as perceptual or otherwise, that account for catchment sponginess and preferential flow?
Yeah, I love that question. Most of the models that we use certainly do not incorporate those preferential dynamics that you just described very nicely. Neither of these plots accounts for, basically water recharging the groundwater without having reached a field capacity. But we know that's not true. We know that below field capacity, especially in really heterogeneous porous media like fractured bedrock, we can have preferential and fracture flow. I don't necessarily believe that this is an impossible thing to incorporate in simple models like this. John Nimmo and others have done some great work on simple models for incorporating preferential transport. There are really, I'd say, like kind of hacky empirical ways to do it. So for example, routing some fraction of precipitation to sort of bypass the vadose zone, potentially again as a function of storage. All those are empirical though, or at least what I've described would be an empirical approach. And I think we would really benefit from an improved understanding of unsaturated water transport in bedrock, at least from like a field and observational standpoint for addressing that question. Generally though, we do seem to get water balance pretty much close to right without having to deal with that complexity. I think it really might be something to consider more closely during low flow periods, during the wet up, for example, in California. But I think, Jessica talked about this in a lot of instances, once watersheds are wetted up, it's more of a question of getting the precip right than it is, calibrating or like perfectly representing subsurface processes. So I think there could be some approach that's, more, I guess, a function of kind of what is your modeling target? Are you thinking about low flows and stream activation during the fall, or are you really trying to predict floods? And I think that my answer to like how to incorporate that preferential flow process might be really very much a function of that modeling target.
Thank you very much. Next questions from Barbara Melvin. Great talk, thanks. About the halfway through your talk, you showed a slide of the CONUS with estimated storage deficit. This showed really strong spatial organization. What sort of data should we look at to predict this? Geological maps, soil depth estimates, something else, all of the above?
Yeah, in some respects, I would say we don't need any map to represent it beyond the map I've given here, because the vegetation to some extent maybe are a representation of the subsurface processes. And so what can we learn from ET and vegetation as indicators of these storage dynamics without having to look beyond that? And the question of how geology, for example, translates into weathering profiles is very much open and is a tough one, and is not, something I'm super familiar with, but the idea that the hydraulic and kind of rheologic properties of rocks affect weathering, and the generation of porosity and conductivity is like right at the forefront of hydrological research. I think that in the eel, we've done, I think, a pretty good job of showing that geology is a good predictor of sponge dynamics and storage capacity. And so where you have those, sort of intensively monitored hill slopes on a particular geology, those can potentially be representative of that larger geological class. But I think that requires careful investigation and validation sites to know that, as Adrian said, you're getting the right answer for the right reason.
Great. And perhaps this is like a follow-up question to the point just you mentioned about the weather and the geology And the question is coming from Charlie Luce, asking any thoughts on where to expect deeply weathered bedrock to develop? Is it all dependent on underlying geology, or are there topography controls and dynamics that might help predict other locales for development of deep saprolite soil profiles?
I think that there's some recent research. I mean, it's old in some respects, but has been revisited by Kieran Harmon's group, showing how landscape relief and some work that Daniela herself has done can hint at the potential structure of the subsurface weathering profile. Hydrological signatures like base flow, recession constants, and those types of things in the stream can also be indicators of some of those subsurface features. I guess that's problematic in terms of runoff modeling. We can't use runoff as an indicator of model input if we're trying to predict runoff necessarily. So that's tricky, but yes, I do think that it's a really tough question though, because again, we're coming back to how do climate, vegetation, rock types, and weathering processes all sort of conspire to produce a weathering profile over long time frames. And all of that can be thrown out the window if you bring in glaciers or something like that have, altered weathering profiles by scraping landscapes clean, for example. Yeah, so I don't know if that addresses the question, or it certainly doesn't answer it, but
thank you. And thanks so much. Yeah. And please feel free, Charlie,
ask more
follow-up questions, through the chat or the Q&A. So moving on with the next questions from Larry Band, who is asking, the deeper forest water use suggests a competition between transpiration and groundwater drainage. Do you think this is occurring, and is there evidence of it in recession curves or in your hill slope position conditions tree water use?
Yeah, that's a really great question. I think what you're asking is, and I think about this a lot in the dry season, like how does transpiration or removal of water from the vadose affect base flows or low flows? And that is, for me, I would say very much like a frontier research question. And that's primarily, the reason it remains a question for me is the lack of observations of deep vadose processes. So how does plant water use in the upper 5 to 8 meters affect drainage from a vadose profile that's 20 meters thick? We could potentially address that with modeling, like a hydrous type approach. The other open question is, where do plants kind of stop competing for groundwater, or rather stop competing for recharge in this sort of implicit way by removing water from the vadose that's dripping down into groundwater, and where do they start directly competing for the reservoir, the groundwater reservoir that's feeding the stream, vis-a-vis the rhyadophytes? And yeah, I'll refer back to this question. I think direct measurements of deficits along hill slopes, and evapotranspiration along hill slopes. Some of the new evapotranspiration data sets are approaching a resolution where we can look along a hill slope to see what the plants at the ridge are doing differently from plants towards the channel. We might be able to sort of tease apart this competition between transpiration and base flow generation or runoff generation, and where it's more of an indirect effect via water removal from the vadose versus a direct effect that is groundwater accessed by plant roots. And I don't think we really know where on hill slopes we have this switch in processes. We don't know, how far up the slope you have to go before the trees no longer have their roots in groundwater, except in places where we've actually drilled and we have observed the depth of the rooting zone. And those places are pretty rare. But this sits at the center of what is by far the most common question I get from managers, which is like, which trees are affecting base flow? What treatments can I put on a landscape to improve low flow patterns? And my first response to that question is, well, which trees are using groundwater and which trees aren't? And I don't think we know the answer yet, but Ying's paper, I think, brought this idea to the forefront. And I think we need to concoct or conceive of some new ways to address it and really classify, even for, Ying's picture here has different vegetation types, but it could just be one uniform tree species along a slope. And we don't even know if that particular species might vary its access to different water reservoirs in the subsurface as you move from ridge to channel. So even just single species investigations of this question, I think are relevant and would be helpful.
Great, thank you much. And since we only have 3 minutes left for this Q&A, I'm asking, we have 4 to 5 questions left, and we will discuss them in the afternoon session, but for now, perhaps we can cover one of them. This one is coming from, I'm reading it in the order. Adrian Harpold, who is asking, how does this deep moisture modeling paradox relate to the old water paradox? How would you explain rapid mobilization of old water for stream flow generation in the context of deep saprolite and rock moisture? Are they consistent, coherent?
I think that, to me, this strengthens the process explanation for the old water paradox. If groundwater is the primary driver of runoff, and groundwater is primarily recharged by drainage from really deep, thick vadozones, based off of tracer data that we have from some of these places, in particular, this site, Rivendell, the experimental hill slope at the Elder Creek catchment that Daniela really pioneered and instrumented, shows that the deep vadozone is much older water. And even though, the recharge is occurring during rainfall events, it's not the rain that's reaching the groundwater, it's drainage that's being triggered due to water potential gradients at the base of the vadozone profile that's refilling those groundwater systems. Following that recharge process, the water itself has to transit the entire hill slope through the groundwater system before it reaches the stream. And so, to me, this is really consistent with the old water paradox. I don't think it's like a new explanation, but it certainly opens up a more coherent explanation for how the water can be as old as it is. And it is very old, on average, months or even years in some of the upland watersheds in California.
Thank you very much, David. And to just wrap up, there was a very one of the early questions that I just missed was coming from Wouter Novin, and who was asking about why was there an image of a sliced cabbage on the observing this pond slide. So
I always forget to imagine the hill slope is a rounded cabbage, and imagine you want to see the layers underlying the hill slope. You slice it open. And so this is a metaphor for the sliced open hill slope, revealing the layers beneath. The knife is our field work.
I think that concludes our morning session, and what fantastic talks and what fantastic discussions and questions, and really gets our juice flowing and ready for more in the afternoon. So I just really want to thank our keynote speakers, because this is not easy talks, not a kind of talk about their own work, and they have to achieve some level of synthesis, our community level understanding of what we know, what we don't know, where are the bottlenecks of knowledge and gaps, etc. So this is, you know, a tremendous effort, time they have put in. So I just want to, you know, ask for a round of applause for our speakers. You know, I know down there we can't hear you, but I hope you you can hear us. And I think I'm going to, we're going to, for those of you who want to stay on in the afternoon, we'll have more discussions. But before then, there's an hour of break from now to 2 o'clock. And Julia, I'm going to let you take over because in order to join the afternoon discussions, and you will need to register. Maybe Julia can send the registration link again. And thank you, everyone. Thank you to the speakers, and thank you to the audience and those who ask great questions. Hopefully you will join
everyone.
us. Yeah, thank you.
Yep, the registration link is in the chat. If you haven't already registered, that's how you'll get your connection information to join that meeting. And we'll get to see and hear from you in that meeting. So we look forward to seeing you then.
Thank you, everyone. I realize Adrian has teaching this afternoon who cannot join us. So we will, I think Sarah will be in the Colorado